Hi there, I'm Mrs. Edwards, and today we are going to go over the intermediate value theorem. You can abbreviate the intermediate value theorem by using IVT. Even on the AP exam, you can refer to it as the IVT rather than writing out the words intermediate value theorem. I'm going to first read you the theorem, and then we're going to dive into what it means. So here's the statement of the theorem. Suppose f is a function that is continuous on the closed interval a to b. If L is any number between f of a and f of b, then there must be a value x equals c on the open interval a to b such that f of c equals L. A prerequisite to using the intermediate value theorem is that the function you're working with is continuous. A couple of ways we know functions are continuous. If you know that the function you're working with is a polynomial, well then guaranteed it is continuous. If you know that a function is differentiable, which frankly we have not gotten to yet, then you automatically know that it's continuous. To be able to use the intermediate value theorem, you've got to start by saying that the function you're working with is continuous, because that is the prerequisite of using the theorem. Here I have some examples of continuous functions. Miles per hour is a continuous function. So for example, let's say that at some time you were going 50 miles an hour and later you were going 70 miles an hour. Well, there has to be some time between when you were going 50 miles an hour and when you were going 70 miles an hour that you were going 64 miles an hour. That's really the intermediate value theorem. If you are going to gas up your car, and let's say that you started with a tank that had 5 gallons in it, and when you finished gassing up your car, you had 12 gallons in the tank. Well, then at some time between when you had 5 gallons and when you had 12 gallons, there must have been a time between those two such that you had 10 gallons in the tank. You don't just have 5 gallons and then bam, you have 12. You have to hit every measurement in between. One more quick example, a corn stalk growing. Let's say that we look at the corn stalk and it is currently 1 foot tall. At a later time, the corn stalk is 4 feet tall. Well, there must be a time somewhere between the time it was 1 foot and when it was 4 foot such that the corn stalk was 3 feet tall. That is the intermediate value theorem. It is important for you to know that the intermediate value theorem, what it's really doing is guaranteeing a height. This is helpful for you to take away that big picture, because if you're on the AP exam and you're asked to guarantee that there is an x value between two x values, such that when you plug it into the function, that guaranteed it's a certain height, you know you're going to use the intermediate value theorem. So intermediate value theorem used to guarantee a height. Here we have the function f of x equals 2x minus 4, and we want to guarantee that f of x has a 0 on the closed interval 1 to 3. We aren't going to actually use the graphs to make this guarantee, but I am going to show you graphically what's happening so you can understand this theorem a little more thoroughly. So here we have the graph of f of x, and we are going to guarantee that there is a 0. So remember, a 0 means an x-intercept. Well, this is another way of saying that we're guaranteeing that somewhere the function x has a height of 0. An x-intercept, a coordinate for an x-intercept might be c comma 0. This is a little bit of, we want to guarantee a height in disguise, because a 0 is an x-intercept, which means the height is 0. Okay, and then we're looking at the function f of x on the interval, the closed interval 1 to 3. So that means that the c value, that's the x-intercept, is not going to be at 1 or at 3. It's going to be somewhere between 1 and 3. Looking at the graph, that means that we are looking from 1 through 3. So we're looking at this graph from this point through this point. You can tell by just looking at the picture that clearly we are going to have an x-intercept somewhere between 1 and 3. Let's go ahead and state our conclusion, like what is it we're trying to prove before we actually prove it. So with all of this written up here, what we're saying is that there exists an x that we call c, and that c is somewhere between 1 and 3, such that when we plug it in, so f of c equals 0. So there exists an x equals c on the open interval 1 to 3 such that f of c equals 0. It's nice to go ahead and state the conclusion because if you don't know where you're headed, it's kind of hard to get there. All right, so then starting at this point, we have 1, negative 1, and then that line ends there if we're only looking on the closed interval from 1 to 3 at 3, 5. Intuitively, if we start to follow along between the coordinates 1, negative 1 and 3, 5, and if we're starting at a height of negative 1 and we're eventually getting to a height of 5, well then we know, since this is a continuous function, that we're going to hit every height in between negative 1 and 5. So surely we're going to hit a height of 0. That is the intermediate value theorem. Specifically, if we stopped, we're looking as we go up and we stop right here, we can see that it actually is going to happen right there. The intermediate value theorem is not about you finding the exact value for c where this happens. You are just guaranteeing that there is some x value between 1 and 3 that when you substitute that number into the function, you will get a height of 0. So if we're going to apply this theorem, the very first thing that you want to do is state that the prerequisites have been met. And the prerequisite for using the intermediate value theorem is that you are dealing with a continuous function on a closed interval. So on the AP exam, if this is a free response question, you must state that the prerequisite has been met. Nowhere in the given information did it say that our function is continuous. But what we can say is that since f of x is a polynomial, we know that it's continuous. Specifically on the closed interval 1 to 3, because if it is continuous everywhere, it's definitely continuous on the closed interval 1 to 3. Okay, the next thing that we need to do is we need to establish a height that is above and below the height we're trying to guarantee. Having a 0, meaning having an x-intercept, meaning establishing a height of 0. We want to establish a height below 0 and above 0. And you're going to use the endpoints to make that happen. So the x value at one of the endpoints is 1, and the other x value at the other endpoint is 3. So we're going to substitute in 1 and 3 into our function there. If I substitute 1 into this function, 2 times 1 minus 4, that's going to give me negative 1. And we're like, yes, it's working because we just found an x value that gave us a height below 0. Okay, next I'm going to substitute 3 into the function and I get out 2 because 2 times 2 minus 4 is 2. Again, we're like, yes, this is working, because in substituting the x values at the endpoints, we found a height that is below the one we want to guarantee, which is a height of 0, and a height that is above what we want to guarantee. Next, we want to formally state that the height you want is between the heights you found. I know it seems really obvious because you're like, well, I'm trying to get a height that is above and below 0, but you need to state it. So we're going to say 0 is sandwiched in between there, -1 and 2. So finally, we can now declare our conclusion statement that there is an x equals c somewhere between 1 and 3, such that when we plug it in, f of c is going to equal 0. But we need to say what theorem we're using, so by the intermediate value theorem. Each one of these 4 things need to be included for you to get the points on an intermediate value theorem free response question. The first time that you encounter a problem that has a table of values, sometimes it looks a little overwhelming, but don't worry, we're going to look at it a piece at a time, and they're not that bad. But it is common on the AP exam that they give you a table of values for some functions rather than giving you the equation of the function for you to substitute numbers into. Let's read the question. H of x and g of x are continuous functions for all real numbers. I'm going to stop there for a moment. Saying that h and g are continuous functions is leading me to believe that we're going to be using a theorem, because continuity is a prerequisite for nearly every theorem. Okay, then the table below has values for the functions for selected values of x, and they're defining the function m of x as h composition g of x plus 7. We have some values. Explain why, or justify that there must be some value c for a c between 0 and 3, such that when you plug c into the function m, you get out a height of 2. M of c equals 2. What you're trying to guarantee here is there is an x value between 0 and 3, such that when you substitute it into the m function, you get out a height of 2. Guaranteeing a height can be done with the intermediate value theorem. Okay, so we've got to start with the first step of using any theorem is to state that we have met the prerequisites for that theorem. And the only prerequisite for the theorem, intermediate value theorem, is that we have a continuous function on a closed interval. The reason that we know, okay, let me back up for a second. M of x, we're guaranteeing that the m function has a height of 2. So we want to be able to say that the m function is continuous, specifically on the closed interval 0 to 3. One way that you can guarantee continuity is if you're looking at the equation and you see it's a polynomial, so you could say, oh, m of x is a polynomial, so it's continuous. Obviously, we don't have an equation here. Another way that you can guarantee continuity is if you were told that the function is differentiable, then guaranteed it's continuous. We have not gotten to differentiability yet, but just kind of file that away, that that's another way we know that the function is continuous. A third way, which is what we're going to use here, is the function m of x was created by taking the composition of h and g and then adding 7. The functions that created the m of x are both continuous, so that means that the function m of x will also be continuous. If you're adding, subtracting, multiplying, or taking the composition of some functions that were continuous, guaranteed the resulting function will be continuous. I like to think of it as if you start with good stuff, you're going to end with good stuff. Now, don't hear me saying if you start with bad stuff, you're not going to get good stuff. You could have a couple of functions that are not continuous and you put them together and you end up getting something continuous. That's a whole different story. But just remember, if you start with continuous functions, put them together, you're going to get a continuous function. Okay, I've said a lot there, but focus. You must state the prerequisite is met. So I'm saying that m of x, which is the function that we're trying to find, m of c is 2. So we need the function m has to be continuous, and I can say the reason why is it's made out of continuous functions. And over here it was continuous for every single number out there, so if it's continuous for all numbers, it's definitely going to be continuous on a smaller interval. Okay, next thing I need to do is I want to establish a height above and below the height I'm trying to guarantee. And I'm trying to guarantee a height of 2, and we're going to use the x values at the endpoints of the interval to establish this height. And frankly, we're kind of crossing our fingers because we're hoping that when we substitute 0 and 3, that we get a height that is less than 2 and greater than 2. If we don't, well then we're not going to be able to use the intermediate value theorem, and we will not be able to guarantee that there is some x equals c out there that gives me a height of 2. Substituting in 0, and we're going to substitute in the x's on the endpoints there, so 0 and ultimately 3. So I substituted in 0, coming over here, look at that, m of 0 equals h of g of 0 plus 7. And then when I want to evaluate this, I'm going to look to figure out what's inside first. So I want to find the answer to g of 0. I can come over here to the table. When x equals 0, the answer to the g function is 2. So g of 0 is 2. So now I have h of 2 plus 7. Now I can find the answer to h of 2. So coming over to the table, if I plug 2 in for x, the answer to the h function is 5. So that's 5. 5 plus 7 is 12. Woo! We're so happy, okay, because we did establish a height above 2. When we substitute in 3, I sure hope that it's below 2. So I'm going to substitute in 3. Now that I'm substituting in 3, coming over here, m of 3 is equal to h of g of 3 plus 7. I can evaluate g of 3 first, what's inside first, so g of 3, plug in 3, the answer to the g function is 1, so this becomes h of 1 plus 7. Now I can find the answer to h of 1. So when x is 1, the answer to the h function is negative 15. So we have negative 15 plus 7, which is negative 8. Victory is ours, okay? We just established a height below 2. So there was an x value, namely 0, that generated a height above 2. There was an x value, namely 3, that generated a height below 2. So next, we want to formally state that we found a height above and below the 2 at some x values on this interval. So I've already plugged in the numbers and shown that, so I'm going to say negative 8 is less than 2 is less than 12. This is an easy one to forget because it seems kind of obvious. You're like, that's why I was doing this. But they don't know that you knew why you were doing it until you make this statement. Okay, another way that you could make this exact same statement is Negative 8, just notationally, negative 8 was the same thing as m of 3. So if you said m of 3 instead of negative 8, and you said m of 0 instead of 12, that would be the same thing, okay? But you would still need to have up here the answers to the m of 3 and m of 0. But just know that if I made this statement here in blue or this statement here in gray, it's saying the same thing. Okay, now that I have stated the prerequisites have been met, I have established that there was an x value that generated a height above 2 and an x value that generated a height below 2. I can now declare, and I'm just going to really restate this up here, there must be an x known as c between 0 and 3 such that when I plug that number in, that c, into the function, I get 2. So here we go. Therefore, there exists an x equals c on the open interval 0 to 3. It's not happening at 0, bracket, because I know when I plugged in 0, I got out 12, not 2. So it's not happening at x equals 0. 3 parenthesis. We're not including 3 because at 3, we got a height of negative 8. And so that's not 2. The x value is somewhere between 0 and 3. And when I plug in that x value into the m function, I'm going to get a height of 2. So there exists an x equals c on the open interval 0 to 3 such that m of c equals 2. And then you've got to state your theorem. So make sure you say by the intermediate value theorem. The formal definition of the intermediate value theorem, hopefully now we can talk through it and you'll understand what all this notation means. Before I do that though, I'm going to try to attach IVT to something because you're going to have a handful of theorems and you want to connect it to something. So far we've had the squeeze theorem, and the squeeze theorem is about finding the limit as x approaches a number of a function, knowing the limit of the function above and the limit of the function below at the same x, as we get close to that same x value. Right, now for intermediate value theorem, if you think of another context where you've heard the word intermediate, like if you are an intermediate soccer player, you are not advanced and you are not beginning. Intermediate, you're in the middle. If you you're attending intermediate school, that means maybe you're in middle school. You're not in elementary and you're not in high school. So intermediate is like in between. And so we are trying to guarantee a height of a function in between a height we find below and a height we find above. So please, when you think intermediate value theorem, you're thinking, oh, I'm guaranteeing a height. Squeeze theorem, you are guaranteeing a limit. All right, so suppose that f is a function that is continuous. That part is saying that the prerequisite to be able to use this theorem is that your original function is continuous, specifically on a closed interval a to b. So a and b are x values. And so if I go on the x-axis to the a and the b, we're only looking at the function between those two. Then if L is a number between f of a and f of b, in other words, L is a height between the height f of a and f of b. You get the height f of a by plugging in the x value a, and you get the height f of b by plugging in the x value b. And so we're guaranteeing that there's this height between these two heights that are created by plugging in those endpoints. Then there must be an x value c. So there's some number c somewhere between a and b. So on open interval A and B, not closed interval, because when you actually substitute in A and you substitute in B, you get this f of A and f of B, and that's not the height we're trying to get. It's something in between, so parentheses, such that when you actually plug that x value in that we're calling C into the function, that you get the height that you're trying to guarantee.